Hello everybody and welcome to the NPTEL online course on microelectronics device circuits, and we take up fabrication processes part 2. So, this is basically the VLSI technology part which we are dealing with. So, there will be 2 modules which we will be devoting to fabrication. Actually it requires a whole set of lectures to go in details of it, but at least for a design course you should know the basic idea of fabrication, and hence this lecture and the previous one. What we will be doing in this lecture series is the outline of the talk will be. So, I will give you certain design rule checks, also known as DRC. So, means that once your design has been done on a simulation platform, your layout has been done, you need to check whether these whether the for example, whether the width of the contact which you have drawn is as per the requirement of the fabrication facility, right. So, it might be true that a fabrication house can only make a contact which is, say, in a very layman language 1 millimeter by 1 millimeter, and you had made 2 millimeter by 2 millimeter. So, it will be rejected once your design actually goes to the fab house. So, the work is that you need to therefore do a checking of your design, and therefore, this is known as design rule check. So, whatever design you have done on silicon using simulation platform tools, you need to do a thorough checking of that. Now, there are 2 types of rules, which is lambda based design rule, which is the first one, scalable design rule, as you can see, right, and we have a micron based design rule, and this is second design rule which you see. So, this is basically lambda and this is basically micron, right, and have been devised for quite a long time, but as the name suggests, scalable design rules are design rules which are scalable, in the sense that if you have a design which is of a higher dimensions, right, say it is 4 lambda, then you can scale it down to 2 lambda and everything will be scaled down by half in a sense. So, that is known as a scalable design rule, whereas what is a micron based design rule? Micron based design rule primarily means that the dimensions of the structures are actually fixed and given to you beforehand. So, you need to fix up those processes. We will be looking into the 4th one, which is basically circuit under test. We will look at some issues of packaging, though itself is again a very big topic, but I will be dealing in a detailed manner later on, but at this stage we will touch and go for the packaging. We will have a look at typical clean room environment which is with us, and then we will look at the finally look at the productivity trend which the current VLSI technology or fabrication gives me in a real sense. So, what is a design rule? First of all, let us see that. This acts as an interface between the circuit designer and the process engineer to satisfy both in achieving high density or performances, smaller design or smaller area, and high yield processes. So, that is what I was saying in the first slide, that basically design rule checks as such that is a common set of rule which a process engineer and a circuit designer both have to follow. So, this is sort of a talking point between the circuit designer and the process engineer, right, and therefore, if a circuit designer follows these rules very thoroughly, then chances are that his design will be accepted by the process engineer and he will be able to send it for proper fabrication. If not, then he has to again iterate back to the circuit designer to change his design rules. Why they are required? They are required because you require a very high performance, which basically means that, for example, I will give you for example, if your contact is very large in dimensions, you eat away into area, but again if it is very small, you then have larger resistance offered by the contact. So, you need to optimize the contact area, and the process people have already optimized the contact area for you. Say the metal contact should be, say, 0.5 micron by 0.5 micron. So, they will let you know, and then you design that much exactly onto your profile and you get the best results. Similarly, since they are already optimized designs, so the area of silicon utilized will be typically very small. So, there will be much tighter design, that is the second point. And the third point is, since the circuit has been based on perfect design rules and they are satisfying the perfect design rules, the yield will be also very high because the production will be also very high. There will be less chances that the fab will fail in delivering the circuit. Now, the fundamental limit or the unity fundamental unity is the minimum line width or the mask dimension. So, this is basically very important. See, you, as I discussed with you in the previous slide, that if you have a, for example, a mask, right, and the mask has got a something like this opening, then you can ensure that, then you can understand that this much amount of mask with this much amount of opening will be actually responsible for all the photolithographic rays to go through us, and as a result you will have an etching table typically available with you. So, the line width which you see here, the minimum line width which can be drawn and you can draw it safely with best results, is basically the fundamental unit, also referred to as minimum line width. So, minimum line width is the available dimension. Who sets it? Of course, it is set by the resolution of the patterning process. Say for example, if you are using optical lithography, where you are shining using an optical light, typically an optical light you are doing it, then the lambda values are typically large, right. So, if you are using lambda large, you very well know that you will have heavy scattering, right, and therefore, if you wanted to grow, let us suppose this much amount of channel length, you might end up growing this much amount of channel length, right. So, what you do to make the design tighter, you lower the lambda value, and to lower the lambda value, you ensure that the lambda value is lower, you have less scattering available to you, you go to E beam as well as X-ray sources. And once you do that, then you are not only able to reduce the dimensions, which is an obvious advantage, but you are also able to make the design much more stable, because for example, if when you have optical lithography, the chances of diffraction at the edges of the mask will be very high. So, you wanted to grow 1 micron, you end up growing 1.5 micron, whereas when you are using silicon or when you are using X-ray or E beam, direct E beam, that is very small, the diffractions are very small, and therefore, the exact length will be replicated on silicon, right. So, therefore, it depends upon the type of source which you are using to a larger extent. Now, this also differs from company to company and the process to process. With the same dimensions, the process will change, and it depends from company to company what type of process flow each of the company takes. Now, therefore, that is what is important, that porting a design between processes is time consuming task, which means that let us suppose today I have a process flow at 180 nanometer, right. I have a process flow at 180 nanometer, right. I want to port it at 90 nanometer, right. This is my job. This porting is quite difficult, because it is not that you just reduce the dimension by half and everything will go fine. No, it is quite complicated, and therefore, it is very difficult to port it from either lower to higher or higher to lower. Now, so therefore, there are certain CAD tools or CAD techniques which scale the design. So, we use scalable design rule. So, I can either use a SCAD tool to do that, or I use a scalable design rule to take care of this thing. Let me therefore come to what is known as scalable design rule. Now, what is happening is that the scalable design rule is that defines all the rules as a function of a single parameter lambda. So, and which can be changed according to achieving the scaling of the dimensions. So, linear scaling, which we say, right. Secondly, for a process, lambda is set to a specific value, and all the design dimensions are translated to absolute numbers, typically minimum line width is to lambda. So, let us suppose I have a lambda, right, process is lambda. So, we define minimum line length to be equal to 2 lambda, there is certain reasons for that. Therefore, let us suppose I have a contact whose dimensions are 2 lambda by 2 lambda. So, this is the minimum contact which you can get. Similarly, you have a polysilicon which is basically say 2 lambda by 4 lambda, this is poly let us suppose, right. So, it will be always a dimension of, so it may be 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6 lambda. So, that is the reason it is scalable. So, once your lambda is defined, you just have to put the integer value to change it from a high to low value, or so on and so forth. Now, and therefore, the problem, the advantage is of course it is scalable, and therefore you can do it, but disadvantage is that it is not scalable over a large range of design, or a very long range of large range, right, because as you can see here that the linear scaling has limited range in dimensions, right, and they are conservative in nature, and therefore their dimension and less dense design is available to you, which means that they tend to give you, though they are scalable, but has a limited range in dimensions, and they also set in non-linearity at higher values, and therefore they are less dense designs with us. Now they generally avoided by industry to a larger extent because of this above problems, and most of the industry uses micron rules for their purposes, right, and they use micron rule quite conveniently in this case. Micron rule is a set of layers, as I discussed with you earlier. So your lambda based design rules are based on the fact that you have a minimum length of lambda, and generally typical line widths are 2 lambda, right, and if you take 2 lambda as your dimensions, and then you take either even or odd multiples of 2 lambda, and you automatically start getting the scaled design. So you can have 2 lambda, 3 lambda, 4 lambda, 5 lambda as a scaled design, and so on and so forth. In the micron based design rule or the micron rules, a complete design rule entities are, they have set of layers, right, and relationship between objects on the same layer and relationship between different layers. So what we do is, in this case we have layers. For example, if you have a you have an interconnect layer, which is the metal layer, then you have a polysilicon layer, then you have a field oxide layer, then you have a silicon layer, and so on and so forth. At each layer we start defining the distance between 2 active points or 2 passive points, right. We can also define the distance between 2 layers across a particular board, right. So what are the constraints? Layer constraints. The layer constraints are, you have CMOS, let us look at CMOS design styles. So substrates are P well or P type, right, and it is N type. For PMOS device, of course, if you remember, substrate has to be N type, and for NMOS device the substrate should be P type, right. So second layer is diffusion or active layer, N plus or P plus, by which you make actually the source and drain region. One or more polysilicon layer to form the gate electrode and serve as interconnect layer, and then this is for gate electrode, whereas this is for metal interconnect layer. So interconnect basically means that so there are 2 layers of metal. One is the metal layer itself, which connects the contact with the external world, and you have an interconnect layer which contacts the external world with the peripheral devices. Now contact and vias, via layer for interlayer connection. So I have a contact, like this, right, and there is a via available here, which starts to make contact with the upper layer, right, makes a contact with the upper layer. So this is known as a via. So via is a sort of a through silicon metallization, right, and that is known as a via, right. Now so we already have an interlayer constraints. Now within the intralayer constraints are, it defines the minimum dimension of the object of each layer and the minimum spacing between object of the same layer. So what does it tell me is 2 things. Micron is what should be the minimum dimension of, for example, an N plus diffusion layer or a P plus diffusion layer, right, and that tells me that. And then secondly, it also tells me what should be the minimum distance between N plus layer and P plus layer, right. I suppose you are able to get the pictures. For example, you are designing a system which is something like this, and you have an N plus layer and you have a P plus layer. Then what does it tell me is, this is substrate and this is source drain, and this is source, and then you have something like this. So what does it tell me is, what should be the minimum dimension of this N plus layer, and what should be the minimum distance between these 2 layers, which is this one, right. If it is closer than this, the design will fail. So 2 things gives you the intra layer constraints in a certain sense. Now to continue with the micron rule process, for interlayer constraints are obviously more complicated, because between the 2 layers you need to talk. Now what are the transistor rules? The first rule is that when an active layer and a polysilicon layer cross each other, we get a transistor. That is a very simple basic rule number 1, right, and therefore the minimum width of polysilicon and the minimum width of diffusion is primarily. So if you have something like this as a poly and you have something like this as a diffusion, then typically this is your active MOS device, right, transistor, which you see. What are the extra rules? Include the spacing between active area, well boundary, and gate overlap active area. So you need to set up what is this distance, how much should be this distance, and so on and so forth. Now contact and via rules. So we have understood transistor rules. Transistor rules are those in which the active and polysilicon layer cross each other, and the dimensions are set by the crossing principles. contact and via rules, well they are formed by overlapping of two interconnecting layers and provide a contact hole filled with metal between the two. So let us say I have one layer here, I have another layer here, we have this empty here, here I fill up with metal, right, and therefore this we refer to as a contact hole, right. Excessive changes between interconnect layer in routing should be avoided. I think this is very interesting and so you might have so I was discussing with you only have two metal layers, right, but you might have multiple metal layers, looking into the fact that you might have multiple interconnect layers, right. So you have one interconnect layer, 2, 3, 4, the last one becomes your VDD layer, which is the final power supply layer. Typically we should not while designing we should not transverse between layers too much. Within the layer we make a design and then we move to the next layer, and we keep these micron based design rules effectively okay with this. Now well and substrate contacts, they should be adequately connected to the supply voltage, as we have discussed already. Failing this will lead to resistive path and lead to parasitic effects such as latch up, right. This is pretty important, and you seldom found problem areas of especially the micron based design rule is if you do not connect your substrates and your wells, substrate and your N well, P well procedures either to the supply or to the ground, and you keep it floating, chances are that there is a problem of latch up. Latch up basically means that maybe it latches to a particular state and stays there permanently, which you do not want it to happen, right. So that is one pretty example, pretty drastic problem which happens due to latch up. So that is what I wanted to say for well and substrate layer, right. Generally your CAD tool for example is performing a functional design check using DRC, and you can use one of the standard cadence for example is one of them which uses the typical layout, does a DRC for you. If there is a problem, it gives you the problem at which point you have a problem in layout, and then you can correct those and again run the DRC. When it is DRC clean, then you freeze your design and send it to the fabricator, right. So look at the second test, as you can see I have got two CMOS inverters driving each other. So this first one is the, let us suppose Q1, and next one is basically Q2. So Q1 is driving Q2, and therefore as you can see here very interestingly that you have a contact here, right, this contact is this one, right, and when the poly and the metal layer, this metal layer and the poly layer cut, this is your basically your MOS device. Similarly this is your MOS device here, similarly this is your MOS device which is M4, and this is your MOS device M3. Since this is PMOS, you will have to, you have metal layer twice the width because you want it to be skewed, you do not want it to be skewed, you want the TPHL to be TPLH, and therefore the width is almost double that of NMOS here, as you can see. So this is your source drain and this is your VDD and ground. So this is your VDD, right, and this is your GND, and this is your VSS or GND, and this is your, this contact is this contact, right, and this contact is this contact or this contact in fact, and this is the source and drain, sorry, drain and source. So you have a drain here, so this is the drain of NMOS, this is drain of PMOS, this is again the drain of source of PMOS, and this is source of PMOS, right, and these two are shorted and I get this. So this one is this interconnect, similarly this is the interconnect which is visible to you. So this is a typical circuit under test, typical layout which you will see here, as you can see here, right, and these are the metal layers which you see, these are the metal layers which you see. So the metal layer is responsible for carrying the VDD. Okay. Well, let us look at the packaging of IC. Well, there are 4 basic functions of the package. Generally you should have pins which will be IO pins, means input output pins. They should exhibit low resistances, capacitances and inductances, so that the delays are minimized across the pin. It should also have a large characteristics impedance to reduce the noise at those particular pins, which is the second part, and intrinsic IC impedances should be high, which we have already discussed the second point, right. The second point is the physical protection. Physical protection means strong connection between die and package and the board. So if you have those try, even if you remove it physically, you can easily remove it. That should not be the case, and it should be properly bound with the board. Now mechanical reliability require good matching between thermal properties of die and the carrier, right. So, that is very important, that mechanical reliability is important, like for example, if there is a shaking of the table or something like that, your die should not be extracted right from the board itself. You should be low cost, the cost factor is pretty important from the industry point of view. Ceramic packages are most superior in performance than plastic packages, but then they are very expensive in nature. So, whenever you go to the fab and you tell them I want this ceramic package, they will provide you a set of ceramic packages. If that matches with your IO of your design, input output map of your design, you can take that ceramic package and do it. So, typically what people do over the years, that if you want a package design, you first look at the package and then you, because if you want to do a package design, then you first of all look at the package, look at the number of pins and IO pins, and then decide how to change your design so that it fits to the package, right. At the last stage you cannot do it. So, therefore, it is always advisable to look at the package first and have a look into it, and it should have industry standards as I discussed with you, right. With IPA production, typically you should be protected from surges, electrical surges and so on and so forth. What is heat dissipation? Heat removal should be as good as possible. So, you should have good heat sinks, and but you can do it by reducing the power consumption, and generally we use mobile computing for saving the power nowadays, right, and most of the time the packages show you packages help you to reduce the power drastically, right. What are the characteristics that affect packaging? Well, of course, what type of packaging you will be using will depend upon the type of integration level which you are using. Similarly, how much wafer thickness are you using, what are the dimensions of the chip which you are using, right, and then it will look into environmental sensitivity. For example, people generally do not like, obviously for obvious reasons, arsenic, lead as part of the packaging technique, and therefore, it is not a very good idea to have these materials as part of the package. And then its physical vulnerability, because how much it is prone to mechanical instability as such. Heat sink and heat sensitivity are two important points, heat generation and sensitivity, in the sense that even if the heat is generated, for example, all mixed signal blocks generate very heavy heat and analog will generate very heavy heat, but then we should ensure that it behaves as a very good heat sink and removes all the heat even before everything comes to the surface. Now, therefore, as I discussed with you, that heat generation and sensitivity are important during operation, since adequate provision must be provided for heat dissipation, right. A passivation layer is grown on the top of the wafer at the end of the fabrication, and we know the reason why, because the passivation layer will be there, it will help you that the lower devices, active devices are not in touch with the active with the environment, and therefore, you do not expect it to get bad. Passivation layer can be a hard layer like silicon dioxide or a soft layer like polyimide, right, and that is quite an interesting one which one needs to look into, that they have a soft layer like polyimide or even a hard layer passivation can be done, right. So, these are the effects of packaging which you see. Packaging processes, if you look very carefully, we generally do wafer thinning by chemical CMP, which is chemical or mechanical polishing. Generally the dies, these are known as dies, and these dies are separated by diamond patterning, you can actually remove these scribes using scribe line, using scribes you can remove it. So, these are actually known as scribe line monitor, as you can see this is a scribe line monitor. Over this you will have a die on this side, you will have a die on this side, right. Good and bad dies are sorted and they are identified, right, and they are identified even when they are in part of the silicon wafer itself. You do die inspection for cracks, physical cracks and defects, and generally we use automated optical microscope, and that is enough to see whether a die has cracked, or if it has not cracked, then is there any physical discontinuity within the package itself, and if there are, it is automatically removed from the system. You have to also have a good process to attach your die with the package, right, and therefore there are techniques of doing packaging packaging and dyeing to a larger extent, and this is quite an interesting or important steps by which you can process these dies. Okay. As I discussed with you, let me just give you a brief of assembly process. As I discussed with you, the wafer, if you look at this is the wafer, right, this wafer is separated using a diamond saw, as I discussed. The separated IC chip, which is this one, is bonded into the center of a lead frame or package. So, I have a chip here and I place it here. These are your IO pins which you see in the back of it. You do not able to see it, but these are the IO pins, and these are the wires which connect the IO pin to the external world. IO pins, and these are gold wires which connect to the external world. So, the pads on the IC chip and the adjoining terminals are connected one by one with gold or aluminum wire, right. So, after you have connected them, the chip is basically sealed. This is the epoxy seal, is sealed with a micromolecular plastic like epoxy resin, and this is the plastic container which you can do it, right. So, this chip, and then you have this is the epoxy resin. So, epoxy resin is over the whole chip, so that it does not get disturbed, right. The lead frame is then cut and bent. So, what you can do is you can cut it and then bend it along this direction, and then you can put the name of the the firm which has made this process, and so on and so forth, or what type of IC is this, and so on and so forth. Its identification mark can be placed here in this case, right. Okay. IC packaging, well, there are 2 or 3 important packaging techniques. The first is the pin through hole. So, the pins are inserted through holes, as you can see here in the circuit board, and soldered in the place from the opposite sides of the board. So, this is soldered from where? So, this is through hole, and then you solder it here, right. And so manual PNP possible, means manual your pin through hole can be possible, and you can actually solder it manually to a larger extent. Then you have a surface mount technology, in which what you do is that so you do have SMT packages or surface mount technology packages that have leads, right, that are soldered to the surface of the exposed metal band. So, this circuit board, you just have to solder it here, right, you solder it here. So, you do not have holes, elimination of holes, that is the first advantage. It is easily manufactured, and you can use both sides of the PCB to do that. They have much smaller dimensions, and therefore, they have reduced parasitics and larger wiring density, and therefore, you do have a tighter control over the wire package, right, and that is what is the advantage of IC packaging in this case. Different types of packages, you can get it on various books. We have a DIP which is dual inline, we have shrink DIP, we do have SK or DIP, and these are all through hole packages, right. So, which means that you draw the hole through the system, through the silicon, and then you wire bond it here, or you can do a bonding here, or you can do a molding here, right, and these are all types of packages available with you. The same surface mount. So, the left one is basically a through hole package, and the right one is basically a surface mount packages, right, and so surface mount packages and through hole packages are available with you, but SMTs give you a much lower parasitics as compared to a through hole, and they are more reliable as compared to through hole, right, and that is what you get from this idea. Let me give you a small maybe a figure or a photograph of the clean room. This is from TSMC, which is basically Taiwan Semiconductor Manufacturing Company, courtesy there. This photograph is there, and basically you can see the clean room. It is filtered such that the particles are 35 particles in per square feet, per cubic feet per unit volume, which means you use a clean room clothing to remove all the dust particles, and there is a airflow maintained, and generally you can have it. So, you generally have clean rooms marked as 10, 100, 1000, 10,000, so on and so forth. 100 basically is the best one, because there are 100 number of particles per unit volume of that area, and similarly 10,000 will also have some particle. So, lower the value, higher is the cost for running cost as well as fabricating a clean room environment, right. So, this is a typical environment which you get in a clean room. Now, the typical productivity trends which you see over the period of year, though this is a bit old data, 2009 data, holding good still, is that the logic is actually growing much faster as compared to the transistor growth rate. It is approximately 58% growth is there in the logic, right, whereas transistor per unit star is relatively smaller, 21% growth is there, right, and therefore higher the complexity, better is the trend nowadays happening. So, yield is getting higher and higher in this case. So, this gives you a basic trend. So, let me recapitulate of what we have done till now. We have understood what are the various design rules, which is one is the lambda based design rule, another is the micron based design rule. Micron based design rule is the most used in the company due to its circuit density factor. Fabrication processes or various IC processes can be analyzed to achieve better review. So, what you do, you just have to go through the fabrication processes. There are certain good books at which if you are quite interested to go through a book, maybe I can give you some idea about the books which you can use. There is a good book by Campbell on microelectronic fabrication, Campbell, right, on microelectronic fabrication, electronic fabrication. You also have a typically SMZ, a good book on VLSI technology, Tata McGraw-Hill, I think, and you have, but this is what Gandhi, there is a book on by Gandhi on VLSI fabrication principles, right, fab principles. But I would recommend that this is quite a heavy book, only meant when you are actually wanting to study deep inside the fabrication. Most of it what you will study in Campbell as well as in Z is also slightly higher. I would recommend at this stage, if you are doing graduation and if you are actually in the first and second year, if you study, have a look at Campbell. If you are slightly ahead and you have done already your bachelor's and you are in masters, try to do Z. And if you are in if you are doing if you are a faculty somewhere or you are a PhD or a postdoctoral, maybe look at Gandhi first of all, right. So, these are the few books which you should be capable or should be able to handle them. We have also understood that that packaging may be given in detail. We have discussed the packaging type. We have understood two types of packaging, through hole and SMT, surface mount technology, and we have seen what the clean room facility typically looks like, as well as the trend in the industry towards logic as well as on semiconductors in general, right. With this, I thank you for your patient hearing. Till we meet next time, goodbye.